My name is Joshua Orman. I'm a prospective member of the Student Information Processing Board at MIT. I have also, since this past summer, been a developer for the Etherboot project, of which Marty Connor is the project leader. Say hi. I'd like to thank him before we get started for his assistance with the demo hardware and coordinating video for this talk. So, first, in the theory part, I'm going to give a bit of a conceptual overview, talk about why anyone would want to do this stuff. What are some of the important parts that need to be understood to be able to set it up for yourself? And some details of how the system boots up, because we're dealing with that quite extensively. Next, I'm going to give some talk about more of the details of network booting technology, how it has been standardized in the past, this wonderful program gPXE that lets us do a lot of stuff beyond those standards, and how you can start up a computer without actually having a hard drive or anything in it, the very initial stages of the bootstrap process. Finally, we're going to do a bunch of demonstrations and talk a little bit about what lies ahead in this field, some of the exciting stuff that's being worked on, and maybe future ideas. We're taking questions and answers throughout the presentation, so if you have any questions, please feel free, raise your hand, ask. I want to make sure that this is understood as well as possible by everyone, and so this is really, I'm trying to tailor the talk to you and to your experience levels, so if I'm going too fast or too slow or whatever, say something, please. And with that, I guess let's get started. The primary motivation for network booting comes from a typical large site. You have many, many similarly or identically configured systems. Each one in the pre-network booting, local booting state is starting up from its own hard drive. But in order for people at this large site to be able to work well with each other, these computers are all making extensive use of the network once they start up. Maybe the user's personal files are on a networked drive, or the programs have to communicate with the central server in order to get any work done. So for that reason, the network is very fast and powerful, can support a lot of traffic, a lot of use. And nothing gets done if the network is down. So most interesting data is stored on the network, not locally, and for that reason, the local drives are basically just used to start up. And it seems, from this sort of way of looking at it, that it would be a great idea if we could be able to eliminate those drives. We already have a bunch of high-performance central servers. And so it's not an entirely infeasible idea to add a bit more infrastructure to that already excellent setup. But there are some problems with this local booting way of doing things, where you start off the local hard drive and then do most of your work on the network. And so I'm going to give a few examples of large sites. One would be a supercomputer cluster. You have 100 or 1,000 machines that are all doing basically the same type of work. They start up and they get some computation to do from a server, and they do it. They might be computing large prime numbers or doing protein folding or any such highly computationally intensive activity. So they start up from their local drives, and then they basically don't use them at all. All the system code is in memory. They're just getting their work sets from the server, computing them, and sending back results. But the hard drives do fail. And while one hard drive might take an average of a few years to fail, if you have 100 or 1,000 hard drives, the time between failures is going to be pretty quick. And so you're going to need to do a lot of routine maintenance on these things and be able to notice when the hard drives fail and replace them, so that when you have a power outage, your 1,000-node supercomputer cluster doesn't only come up with 700 nodes. And in bulk, hard drives are pretty expensive. I mean, a hard drive might only be $60, but if you buy 1,000 of them, that's $60,000 you could be spending on better infrastructure, more nodes for your cluster. Or consider an office building. Employees, they're all doing work using the network and centralized resources, but they like to customize their systems. The IT department is focusing on trying to manage upgrades with all these customizations, and as is inevitably the case, when we say customize their systems, we really mean break their systems, because that's what happens a lot of the time. So for this reason, distributed upgrading is really hard, because everyone's system is a little bit different. And a Windows patch that installs fine on most of the office might have conflicts with 20 machines, and those all have to be resolved independently. There are ways of solving this, but they're also complicated. Or think about us here at MIT. We constantly have new systems going up that need very similar or even identical configuration. We have large public access clusters. All of those machines are identically configured. We have machines in labs and offices. And basically anything that's using Athena has a very similar configuration, but needs to be installed separately and maintained separately. And that can be a pretty big burden. We also have a situation where students often come in with, say, a laptop running Windows or Mac OS X or something, and they're in a class that requires running software on a Linux environment, or vice versa. I know mechanical engineering students often have to run SolidWorks, which only runs on Windows. So it might be useful if there was a way they could start up into a different environment to be able to run that program, but without disrupting how they like to use their computers. The big idea with network booting is you get rid of the client machine's hard drives entirely. Or, and maybe you just start up from an external source that doesn't access the hard drive. So instead of starting from the hard drive, clients execute a small bootstrap program that's stored in read-only memory on the computer. It's burned into a flash chip. So you don't need the hard drive to start up the system. The BIOS can do it for you. That little bootstrap program does some network auto-configuration through a method we'll talk about later, fetches a kernel file or whatever other initial files are necessary to start the system, and transfers control over. And then the system, to access all of its files, mounts a networks drive to get all those files instead of trying to use the local hard drive. For large sites, this has a lot of advantages. Files that are the same for everyone only exist in one place. Every single person doesn't have a different copy of some core Windows DLL. They're all on the centralized server. There's one copy of it. And so when you need to upgrade that, you only have to upgrade it in one place. And in terms of a budgeting perspective, that maybe the additional infrastructure upgrades that are needed for the network to support this are more than compensated for by the fact that you no longer have to pay for, manage, and troubleshoot the individual drives in all your multitude of client machines. And there's also some advantages for occasional use, which is that clients can netboot into a special environment without changing how their primary system works. The example of a mechanical engineering student who needs to use SolidWorks in Windows, you can imagine the mechanical engineering department setting up a way for that student to network boot into a simple install of Windows that has SolidWorks and can save the files to their Athena home directory so that they can easily use it when they need to, and they don't have to reformat or repartition their drive in order to be able to satisfy their course needs. And for system administrators, you can network boot diagnostic tools. So you have a hardware problem. Instead of carrying around a whole bunch of CDs with different tools, you might be able to boot into a menu that will offer you some choices loaded over the network that can run diagnostics or reformat the drive or things like that. And we are going to give an example of that later. But most of all, the reason why I am so interested in network booting, it's fun. There's something intrinsically pretty cool, I think, about being able to start up a computer without a hard drive, being able to use a network for absolutely everything the computer needs to function. And there's a lot of great technology in the area. Yeah, please. Are there any questions? Everything's good so far? Great. So we're going to talk about some of the essential pieces here. Networking basics, since I know some of you might not have a lot of experience with computer networks. The idea here is that a network is layered. You have the link layer, which is basically the physical transmission of electrical signals that links hosts that can communicate directly with each other. You have maybe a bunch of hosts are connected by a switch, like this one, so that they can all talk to each other just by electrical signals. There's no higher level processing that needs to be done. Ethernet is the most common link layer, and those cables will be called Ethernet cables. Above that, there's the internet layer, which connects those subnets together. You have these machines called routers, which route packets between two subnets, and the packets have information embedded in a header that shows where they're meant to go, and that can be used to decide what the next hop of the packet should be, and so on. Basically, the only internet layer used is the internet protocol, IP. Above that, there's the transport layer, which provides data integrity, making sure that everything got there okay, multiplexing, being able to access multiple services on the same host, and connection semantics. So the idea that you're not just sending random packets of information, you actually have a reliable stream that you can transmit a bunch of stuff, and the transport layer will handle breaking it up and making sure it all gets there. There are two main transport layers in use. The complex one is the transport control protocol, which basically does everything you would want for a connection stream. It's reliable, it arrives in order, and there's no duplicates, and you have a stream semantic. You can send a whole bunch of data down the pipe, and TCP will take care of making sure it gets there okay. On the other end of the scale, there's the user datagram protocol, which is unreliable transmission of independent packets. Basically, all that it does is make sure that you don't get things that are corrupted, and it provides the multiplexing semantics, so you can run multiple UDP servers, servers for protocols that use UDP. And when you're dealing with protocols on UDP, you have to handle the fact that packets might be lost, duplicated, reordered, etc. And finally, above that, there's the application layer, which is the really interesting stuff. It's your web server, your file server, your mail server, whatever.
What protocol does web servers use?
Web servers use a protocol called HTTP. It stands for Hypertext Transfer Protocol. It's a protocol that, because web servers often have to handle thousands of clients at the same time, maybe, there are very highly optimized and efficient servers available for that. When you want to, say, boot 1,000 computers at the same time, HTTP is therefore a common choice to be able to use, and that's one of the things that gPXE gives you. We'll talk about that later. This is a example of how locally booted machines auto-configure their network interface. This is some output from a program called DHClient, which handles DHCP. The exact text of it is not relevant. I just want to point out some features in how the exchange occurs. DHCP is the Dynamic Host Configuration Protocol. It's used, basically, there's a central machine that hands out network addresses so that each individual computer doesn't have to know its own address. This,
like to do DHCP?
no, it's fine. The client knows nothing about its role in the network, so until it contacts the server. It's sending packets on this broadcast address, all 255s, which means anyone, anywhere. If you're running DHCP, please give me an address. The server, in this case it's 18.181.0.221, supplies some network configuration info to each computer, and that network configuration consists of an IP address and also information like which router to talk to and so forth. The systems, in order to help the server differentiate between them, send their MAC addresses. The MAC address is a unique hardware-level address that's burned into each network card at the factory. So, and no matter what, any two systems on your network will have different MAC addresses. However, the MAC address doesn't have any structure to it. It's basically 6 random bytes. So MAC addresses can't be used for routing packets. You wouldn't know where this computer is in the world. So you need these higher-level addresses with the structure, the network addresses, IP addresses, in order to configure your network interface. Is that fairly clear to everyone? OK. For network booting, we use the same protocol to get the network information, your IP address, your router, information for how to look up names in the domain name service. But you need more info because you're also loading some files. So there are these additional DHCP options. An option is just a field in the DHCP protocol that can be used to convey additional information. You have the next server option, which specifies the server to load files from. You have the file name of the kernel image to load, file name. And you have, you have the path to a remote disk to boot from. I'm going to talk about that soon. There's something called SAN, Storage Attached Networking, where you can basically have a hard disk that is attached to a network server such that any machine that connects to the server can access that disk almost as though it were a local disk, using the same types of access, and that can be very fast. So with this information, the bootloader configures its network interface and initiates a TFTP connection to the file server. TFTP is the Trivial File Transfer Protocol. It's an extremely simple protocol used to fetch network booting images. It's simple because the bootstrap code is often very small. It might have to fit in a 32 or 64 kilobyte ROM image. And so the less needs to be done on the client, the better. But I'm sorry. There's also an extension called Proxy DHCP, which is useful in some environments where the central DHCP server can't be modified, either for policy or for technical reasons. Proxy DHCP allows you to put another server on the network that just responds to network booting requests, giving the file name and server and such, and allows the existing DHCP server to give IP address, router, and so forth. I mentioned network attached storage. It's the SAN thing. So in this is the case where the server provides a hard disk image to clients. And that has a lot of advantages. First, there's a very light CPU load on the server. But the clients gain the benefit of the fact that many people might be accessing similar data on the server. The server can keep that data cached in memory, so it doesn't have to actually incur hard disk latency. It's just network latency. And networks are actually faster than hard drives these days. You can also have, since you're using one central machine, you presumably have a fairly significant budget to spend on that machine because you're saving the money on all the client drives. And so you can invest in a very high-speed, redundant array of disks. And so you get reliability, you get higher speed, and you have a fast network. So you might actually get better performance than booting locally. If you're booting Windows, you can't boot Windows from a standard network file system. Like at MIT, we use AFS, or Windows people might be familiar with SMB. Windows can't boot from that, but it can boot from a SanDisk. The problem is that two clients can't write to the same image. Because if they were to do so, they would possibly trample over each other. There's no intrinsic locking mechanism. For this reason, often people use a hybrid approach, where the root file system, containing all the system files, which presumably won't need to be changed during boot up, and then you use a more standard network file system, like NFS, AFS, or SMB, for user data. Is that clear? People have any questions so far?
You may want to point out for interest that a lot of this protocol stuff was invented
At MIT, yes. The AF,
TFTP was, for example.
So, but the problem is that some systems want to be able to write to their root file system. They want to be able to update the registry, say, if you're booting Windows. But it's inconvenient to have to supply a whole separate image for each system. You lose almost all the advantages of network booting, in that you have only one thing to update and so forth. So there's this technology called copy on write. As we know at MIT, if at all possible, involve cow. But in this case, one read-only image is provided to all clients, but it looks writable. The client feels like it is told that it can write to the image. It sends its writes to the server. But the writes actually go to a separate file, which is unique to each client. It only contains the modified information. That file, maybe you'll have a 20 gigabyte hard disk, but only 10 megabytes of data is written during boot up. So you have 20 gigs shared between all clients, and then 10 megabytes for each client. That's very scalable. When the client asks for something from its disk, if that block has been written by it to the cow file, then the block is served from the cow file. Otherwise, it's served from the base image. And this makes upgrades very easy, because you can usually simply blow away all the cow files. The clients will still boot up fine from the base image. They might lose a bit of customization or remembering when they last booted or some such, but that's not usually important. And that means, again, you have only one place to upgrade, which is very advantageous a lot of the time. So that's sort of the end of the stuff on the essential pieces of network booting, or of this networking stuff that's essential for network booting. Does anyone have any questions so far? OK, we'll move on to some information about the system boot process. Inside your computer, there is a chip called the BIOS. It stands for the Basic Input-Output System. And it's the very first thing that's run when you start up the computer. Before any operating system is loaded, before you even see text on your display, the CPU jumps to a location in the BIOS, and the BIOS starts executing doing its thing. Its main job is to initialize the hardware. That part's called the power-on self-test. It catalogs boot devices and picks one to start an operating system from. This picking might be helped by the user. You might have experience with having to go into your BIOS setup to ask it to boot from a CD if you're installing a new operating system. So, so the BIOS doesn't know everything. One of the things it usually doesn't handle is networking. So there's this expansion ability called an option ROM. You can have add-in cards with option ROMs on them that allow BIOS functionality to be extended. These are just additional read-only memory chips on the cards that the BIOS initializes during the power-on self-test. And these ROMs do their thing by hooking interrupts. They can provide access to a new type of hard disk. They can trap the boot system call to do a different type of booting, say network booting. And on newer systems, they can actually just say, I'm a boot device. Put me in your menu alongside hard disk, CD-ROM, and so forth, and call me if the user wants to boot from me. These interrupts, by the way, are a pretty important part of the early boot environment. Instead of having the BIOS have all of its internal, all of the functionality for reading from hard disks and such internal, it provides traps that allow these to be executed. So a program running under DOS, which runs basically in this environment, can execute an int13 call to access the hard disk, and it doesn't have to handle talking to the disk driver itself. And also, an option ROM can change what int13 does. So instead of going to the BIOS's code for accessing the hard disk, it'll go to some code for accessing a network disk if that was configured, and the BIOS disk if not. After the BIOS, we have some initial bootstrapping. This is the part that's called usually a bootloader. This occurs in a mode of the CPU called real mode. which means it can use the BIOS and option ROMs, but it's limited to a megabyte of memory. So this is just for initial loading. The goal here is just to load enough for the operating system to manage the rest on its own, which means you need to load enough for the operating system to be able to access the rest of its files. So you need the kernel image, which is the central code that runs the operating system. You need device drivers for your hard disk if you're booting from a local disk, or for your network card if you're booting from the network. You need file system drivers so you can understand the directory structure on the hard disk. And if you're booting from the network, you need a network layer that handles that Ethernet, IP, TCP, and such. For booting the Linux operating system, this is handled by packaging the kernel image, and everything else is in an initial RAM disk, which basically consists of a bunch of drivers as kernel modules, and some small amount of code to load them all and wire everything up, and find and pivot to a root file system. Maybe it's on the network, maybe it's on a local disk. For Windows, it's kind of complicated. There's not really much good documentation on exactly how it works, but there's a way of marking drivers as as able to be loaded at boot time, or suggested loaded at boot time. And during this real mode initialization, all of those will be loaded so that they can be used in the operating system in its mystical process of finding its root file system. But to do anything useful, the operating system needs to switch out of that boot time real mode into protected mode, where it can't use the BIOS or ROM services. Protected mode is necessary if you want to access more than 1 megabyte of memory, if you want to be able to run multiple things at the same time, if you want to be able to deal efficiently with numbers larger than 65,000. Real mode is extremely, extremely limited. Once real mode loading is done, all those drivers that were loaded are used so that the OS can make its own connection to the boot device. If it's booting from a local disk, it starts accessing the hard disk by sending the commands to the drive directly. If it's booting from the network, it starts, say, an iSCSI connection to a network disk. I'll talk about iSCSI later. It gets to a point where it doesn't have to rely at all on the code that was provided by the option ROMs or the BIOS. This results in much better performance, because the operating system kernel is not limited by the boot time size constraints. It can have optimizations that deal with corner cases in a fast way, that are just more complex, so that they're not as slow. It also avoids resource conflicts. If you had the OS calling out to boot time code to access a hard disk that happened to be on the network, and the OS was also accessing the network because you had your web browser open, that would basically you would have two things that didn't know about each other, each believing they were in sole control of the network card, and you would probably not get anything out at all if the system even survived. So it's important to perform the switch. But how does the OS know where to look? Well, that depends on the operating system. One way is to have a kernel command line, where in the bootloader, when configuring the bootloader, the user specifies some options to the kernel that will tell it where to look for its hard disk. In Linux, you would have the root equals /dev/sda1, for instance. Or you could have a boot firmware table, where the bootloader leaves info in a special table so the kernel can find it later. This is often used in network booting scenarios because a lot of the time you don't know exactly what the parameters are that you're going to pass to the kernel. You don't know what IP address the system that's booting the OS is going to get. You don't know exactly what drive it's going to boot from. It might be something that's configured at runtime. So the kernel searches through low memory for a specially formatted table that will tell it all that information. In general, Linux boots use the kernel command line, and Windows boots rely on boot firmware tables because Windows doesn't provide much way of specifying boot locations explicitly. But some boot firmware tables can also be used for auto-configuration in Linux. Is that pretty clear to everyone? OK. Now we're going to talk some about network booting technology and start with sort of a brief history of it. In 1993, here at MIT, actually, Jamie Hoffman created the NetBoot image proposal. It was the first attempt ever to describe a mechanism at netbooting. And there was a very simple reason behind it. Jamie had 2 computers and 1 hard disk, and he wanted to be able to use both computers. So because this was sort of an ad hoc design, the protocol was very simple. The Bootstrap loader fetches, using this trivial file transfer protocol, something called a network boot image, NBI. It's a new file format. It describes how to transfer control to the kernel and drivers, and it bundles the kernel and those drivers. So you only have to load one file, look at how it says to put things in memory, and then call it. there's no callback interface. So the boot code doesn't have to stay around wondering if the kernel is going to ask it to load some more files. It just loads and goes. And so pretty soon, in 1995, Etherboot, the very first program created by our project, was released, capable of booting NBI images. So this was used very happily for a while. And then Intel came on the scene. And they said, this is too simple. Some people aren't being able to do what they want based on this. We should make a better one. And they created the pre-boot execution environment, which is extremely complex. But it can be used in a simplified form. Instead of just specifying the file to load, the DHCP options contain a boot menu. Select this if you want Windows A. Select this if you want Windows B. When you pick something from the boot menu, that doesn't tell you immediately what file to load. That tells you the address of a server to contact so that that server can tell you what file to load. Once it tells you, you can download the file called a network bootstrap program from using TFTP. But that's not, and then you execute it. But that's not it. There's a callback interface. The NBP can call back to the bootloader and say, I want more files, or I want to know what my network configuration is. So the bootloader has to stay around and provide all those interfaces. Also, this was horribly specified. The specification is extremely unclear in some areas. There's actually 2 separate operations that are represented using the same numeric encoding, so it's impossible to handle both. But it's Intel. PXE is standard now. Every network card you might buy will come with a PXE ROM, and if you put it in your computer, you can boot over PXE. And MIT has a PXE boot service. You can start Windows, the Debathina installer, a partition tool, etc. But PXE has some problems. It's poorly specified, so everyone sort of implements it in a slightly different way. And this means that code that a network boot program that might run fine on one machine will have subtle problems on another. So you need a lot of very robust coding and debugging to make things work. It's also limited to using TFTP, which is slow and doesn't scale well. Because TFTP is based on UDP, the user datagram protocol, which I mentioned earlier is unreliable, it has to work in a sort of lockstep to make sure everything gets there. The client asks for a data block, the server sends it. Repeat ad infinitum, and resend after a few seconds if it didn't get there. So you incur round-trip latency both ways. Any network boot program wanting to load files using a faster protocol, one using the transmission control protocol, which handles this stuff in a very efficient way, would have to implement a full TCP/IP stack. This is quite complicated. This is not something that was normally done in boot code, especially because NBPs were officially limited to 32 kilobytes. It's rather hard to squeeze much of anything in there. There's also the problem that the netboot image format was pretty lightweight. It was easy to automatically wrap a kernel and drivers into one bootable file. You wouldn't have to do much more than that. An MBP is a program. It has to be coded to download more files. So you can't simply say, OK, I have this kernel with these drivers, load that. You have to write the program that does that. And that's pretty annoying and time-consuming. In 1999, the HP Peter Anvin and the SysLinux team came out with PXE Linux, which is a PXE network bootstrap program for loading Linux. It's very, very easy to use. It uses this unified configuration format, the same thing as many other bootloaders. It's like SysLinux, ISO-Linux, which is used by all Linux distributions for booting from a CD-ROM. And it's a pretty simple configuration file. You specify a kernel and an initRD, some command line arguments that are used by the kernel in figuring out how it wants to do things. And there was much rejoicing, because you now could PXE boot Linux without writing a PXE netboot program yourself. This is very good. 10 years later, PXE has never been updated. The 1997 specification still stands. And this is largely because Microsoft, which is a pretty close ally of Intel, doesn't really like centralized booting. They like everyone to pay for a separate Windows license. But networks are much faster these days. We have gigabit Ethernet. They're more ubiquitous. A lot more places have extremely strong network infrastructure of the sort that I mentioned on the first slide. Thin client applications are much more popular. Thin clients are situations where the client machine isn't really meant to be a full working computer. Oh, well, working, obviously, but not full. It's meant to do a very specialized task. I gave you the example of supercomputer machines. You also have point-of-sale terminals, the machines that are used in grocery stores to check you out. You have maybe classroom machines that are specialized for a particular educational goal. You have many ways that you might want a simpler system that doesn't need as many resources. But you would still otherwise have to include a full hard drive and everything. So network booting would be good for that. And people just want to do more. It's a cool technology. There are a lot of uses for it. Etherboot project to the rescue. We have been maintaining, developing a better net booting program. It's called gPXE. It's an extensible, powerful, open source network bootloader. And it does a ton of stuff that PXE can't. It has drivers for dozens of network cards, so you can probably use it on yours, including almost all the cards that are in common use. There are a few that we're still working on. It has stacks for InfiniBand, which is a very high-end 10 gigabit fast network stack, and 802.11 wireless, the thing that your laptop uses to talk with the MIT network, so you can boot wirelessly. It has a chain loader for vendor PXE that uses the PXE network driver. So if you have an existing PXE infrastructure, or if your network card isn't supported by gPXE's native drivers, you can load gPXE from vendor PXE, take advantage of its special features, and basically make your booting better. It has a complete, robust PXE stack for clients. It's free of many of the bugs that are found in network card PXEs. It has a complete TCP/IP stack. You can run HTTP. It has a DNS resolver, so you can use host names. You can say boot from installer.mit.edu instead of saying boot from 18.7.21.127. And it supports many protocols for downloading your image. It supports TFTP, like PXE does. It also supports HTTP, the web protocol. It supports secure HTTP, so in case you want to make sure your image isn't modified in transit, or if you want to use user authentication. It supports the file transfer protocol. It supports loading images straight out of a network file system. And it supports booting from SanDisks, which vendor PXE does not unless you buy like a several $100 network card. You can boot from iSCSI, HCA over Ethernet, even the SCSI RDMA protocol for InfiniBand, which I believe we are the only network booting firmware to implement. We support loading many types of images, not just PXE netboot programs. You can load something in the executable loading format, which is a pretty generic way of packaging an operating system kernel. COM32 modules that are used by syslinux, which do interesting things like show menus. You can boot multi-boot images, another generic kernel format. The NBI format that was used by the original Etherboot. You can boot PXE netboot programs, and you can also boot a Linux kernel directly. And there's a command line with scripting support. So you can implement complex boot policies like associate with this wireless network if it exists, and then try booting from it. But if you couldn't get on the wireless, try booting from the wired network. And if you got on the wireless, download this file. If you got on the wired, download that file. So as I mentioned, one of the things gPXE can do is boot from a SanDisk. And so because of that, I'd like to talk a bit about how SAN sort of works from a configuration point of view. You can start a SAN boot in two ways. You can set the DHCP root path option that I mentioned, or you can use the SAN boot command from a gPXE script or from the command line. There are two SAN boot protocols that are mainly used. There's also the InfiniBand SRP that's really high-end. iSCSI is basically SCSI over the Internet Protocol. SCSI is a standard way of attaching hard disks inside a computer. It's routable, which means you can boot off a server on the other end of the world if you want to. It's reliable, runs over TCP. It's kind of complicated, and there's some overhead in terms of speed. You can't quite blast your data as fast as possible. On the other end of the scale, HEA over Ethernet. HEA is also an internal hard disk attachment scheme. It's unroutable. You have to boot off a computer on your directly physically communicating subnet. It's a little less reliable in terms of because there's no it implements its own consistency checking, so you're not going to run into huge problems. But it hasn't really been designed to the scale that iSCSI is. But it's very simple, and you can blast data absolutely as fast as your networking cables can carry it. In order to boot off either of these, you name a server using this root path. An iSCSI root path is very long. An HEA root path is 4 characters. iSCSI, you specify your server. It can be an IP address or a name, colon, the protocol, which is always 6 for TCP, so you leave it out, colon, the port, which is always 3260, so you leave it out, colon, the LUN, which is always 0, so you leave it out, colon, and then this thing called the IQN, or the initiator qualified name, which is a slightly strange way of naming a disk to boot from. The idea, for some reason, is that these are supposed to be globally unique. So you say IQN dot, and then you have the year in which you obtained your DNS name, dot. And then you have your DNS name reversed, so it's hierarchical, colon, and then the name of an image that you're booting. In theory, if you had an iSCSI name server, you could boot using just this thing. You wouldn't need to specify the server. But since it's unnecessary overhead to do that, we have this silly long root path. And really, you can use anything you want in this field. It's just this type of name is a conventional way of naming a disk, which probably could be named using just DOS boot in this case. For AOE, every disk on the network is addressed by a combination of a shelf and a slot. In this case, the shelf was 1 and the slot is 3. You put an E in front for historical reasons. That's very simple. And also, I mentioned scripting. gPXE scripting is extremely powerful, and there are a ton of situations that you can use it with. And this demonstrates some of them. I'm going to explain each of these scripts. The first script is for booting PXE Linux over HTTP. PXE Linux is a PXE netboot program, which you would expect to mean it could only use TFTP. TFTP is kind of sucky for booting large amounts of clients at once, because TFTP servers aren't designed to scale well. The protocol is very simple. PXE Linux, though, has some support for detecting whether it was loaded from gPXE, and if it was, using gPXE's extended protocol support. So every gPXE script has to start with a pound bang gPXE. If you've done Unix scripting, you may recognize this as very similar to the shebang line. The idea here is that because this is sort of a magic number, so that gPXE knows that something is a script and should be executed as one, as opposed to checking whether it's another type of image. There's a set command, which can be used to set various settings. You can set DHCP options by number. In this case, 209 is the DHCP option for setting the root of the PXE Linux directory, where PXE Linux is going to look for its configuration file and such. Normally, that's guessed based on a TFTP setup. If you set it to http:// something, PXE Linux will say, hey, I was booted from gPXE. I can actually access this using HTTP. Because it's a DHCP option that gPXE itself doesn't know the format of, you have to say, colon, it's a string. The chain command is very common in scripts. That basically says download, load, and execute this image by gPXE. This is the last boot from this image. A chain comes from the expression chain load, which is where the bootloader loads another thing in its place. You use a $ with curly braces to interpolate the value of a setting into a command. So this will chain load http://my.server/netboot/pxelinux.0. Is that pretty clear to everyone, how that script works? Okay. Next one is the script for a program called gPXE Linux, which attempts to get at the idea of this type of setup, but in an easier format. gPXE can embed images. You don't have to load your images over the network. gPXE Linux is gPXE with this script and pxelinux.0 embedded, so that you can plug it straight into a normal PXE setup, but gain the benefit of gPXE's protocol support. So first, we run DHCP on the first network interface. Network interfaces are named netx, where x is a number starting with 0. Next, we load the embedded PXE Linux image, and then we boot it. Oh, sorry, and then we boot it. And there's nothing actually. The only thing done with the network in this script is running DHCP, so that PXE Linux can use that networking information. The assumption is that the whole gPXE Linux thing, which includes gPXE, this script, and PXE Linux, is going to be loaded like a PXE netboot program from a vendor PXE stack. So you can use scripting to do things like that. This is a script that I'm going to use in one of my demos later. This is for doing a wireless boot at MIT. Wireless, you can't quite completely auto-configure it because you need to know what network to associate with. You can't just go based on what cable is plugged in. So you have to set the SSID, which is the, I forget what it stands for, but it's basically the term for a wireless network, to MIT, which is our network. And then you execute auto boot to say, OK, now start booting like you would if there was no script. Settings that are specific to a particular network interface are named net whatever slash, and then the setting name. So when you're booting from net 1, gPXE will check net 1 slash whatever settings before it checks just the name of the setting. And then this final script is an example of a complex boot that uses a static IP. This is a case where there is no DHCP server on the network. And you can still use gPXE to boot in that case. You just have to specify all the parameters by hand. You have to set the IP address, the gateway or the router, the net mask, which specifies sort of how big your local network is, and a DNS server if you want to be able to use named host names. And then you have this IFOpen command, which says, OK, I've set all the settings. Now bring up the network interface so I can use it. You load, in this example, a Linux kernel and an initrd from a web server, and then boot it. The initrd here is not just an image. It's actually loading a PHP script, and it's passing a parameter to it. That parameter is the MAC address of the first network interface. And this could be used. You could have a PHP script on your web server that parses the MAC address maybe against a table of clients in your site that and determines what type of network drivers are needed for that client and embeds those drivers in the initrd on the fly. This has less load time over the network and might have some advantages when you're doing complicated hardware configuration. gPXE can do this because web servers have extremely good support for dynamic content because web pages use it all the time. So do some dynamic content for net booting. So those are some examples of gPXE scripts. You'll see a couple more during our demonstrations. Is there anything in particular that you're curious about how it would be done that you can't see so far how it would work using this technology? OK. Now we're on to details about storing the boot code. How you get from your BIOS into this nice gPXE environment. Well, the easiest way to do it is to do a PXE chain load. Almost every network card in existence, as I mentioned, has a vendor PXE stack. So the idea is that if you package gPXE as a PXE netboot program, then the vendor PXE stack will load it, and gPXE can take over and provide all its cool stuff. And you don't have to then go around to all the machines and flash it into a ROM image. gPXE has an UNDI driver. UNDI is the Universal Network Device Interface. That allows a special gPXE if you create, you just ask for undiionly.kpxe, to work even on network cards that gPXE doesn't have drivers for. Normally, if you load the normal gPXE PXE, it will attempt to use its own native drivers, which are usually faster and better. They allow using multiple network cards for one. But it's always possible to use the same network card as the vendor PXE stack that loaded you. And that's often useful on strange hardware. So the way you do this is you would configure the DHCP server to choose how it boots its clients based on a parameter called the DHCP user class option. If there's no user class, which is the case when you're booting from a vendor PXE stack, the DHCP server will hand out the gPXE image and say, boot this. If there is a user class, gPXE provides a user class of gPXE, as you might guess. Then the DHCP server can hand out a different image, like boot this gPXE script, or boot PXE Linux over HTTP, or boot from this SanDisk. So that helps you get some excellent customized booting processes in an environment without actually changing the individual client machines. You just configure them to boot from network in the BIOS, and your setup on your DHCP server will do all the rest. Is that pretty clear? I know this stuff can be kind of confusing. I don't want to be like rushing too fast for you guys. It's all okay? Okay. The other option is to burn the netboot code into an option ROM. You can store it in a flash chip on an expansion card or in the BIOS directly. We're going to have some demos of that. So you can, in all of these network cards, or almost all modern network cards, have electrically erasable ROMs, EEPROMs. So you can flash new images on. You can flash gPXE in place of the vendor PXE stack. The ROM image has to identify the PCI device it's associated with. So you have to build a special ROM for every different PCI device that you might want to, well, every different type of network card you might want to use. But we'll show you later there's an automated tool for doing that. BIOS and the ROMs execute in real mode. As I mentioned before, only 1 megabyte of memory is accessible. And there's an even more stringent limit, which is that the total size of all ROMs in the system can't exceed 128 kilobytes. The video card is an option ROM, and it usually takes up around 50 to 60 kilobytes. For this reason, we have an extremely tight code size budget in gPXE. Any feature that makes a default build go over 64 kilobytes is basically not going to get in, because there are so many systems where a ROM of that size would just not be bootable. A partial solution is to allocate more space with the Post Memory Manager, which is supported by all recent systems, and move some code there to make room. That helps if you have, say, 3 network cards with gPXE on them, or a network card plus some RAID cards, which often also have ROMs to allow you to boot from the RAID. But you still have to be able to fit the ROM into memory when you load it. Unless you have a really new system with PCI 3.0, in which case the ROM is loaded somewhere in low memory, it can do its moving thing, and then move just a small stub into high memory. Move just a small stub into the 128 kilobyte ROM space. So this is becoming a bit less of an issue, but it's still sometimes you'll need to go through and disable a few features to get your ROM in the size you want, especially if you have a card like the Intel E1000 whose driver is very complex. Now we're going to do some demonstrations. You can boot off a server over HTTP across the world. This one's in Oregon. It loads a simple, here, I'll fetch the script for you. Oops, sorry. This is the script. It's got shebang gPXE. It loads a kernel with a simple root argument, loads an inrd, and boots it. And this is how it works. Oh, OK, well, it looks like it already booted. Excellent. OK. Here in the EtherRoot project, we are big on transparency. This is why our booting machine is transparent. You can see there is no hard drive anywhere in here. There is no CD drive either. There's just a couple of NICs, a CPU, a motherboard, a power supply, and some memory. It's very simple. It's basically the simplest type of system you can work with, and we're going to do many interesting things with it. It also has a slightly broken power button. So here we have the BIOS, the post screen and the BIOS. And gPXE is burned into a ROM on this system. So when the BIOS looks around and finds no boot device apart from this one, it executes it.
Hi, I'm gPXE.
And there is a possibility to break to a command line there if you want to run some custom commands, boot from something that's not offered by your DHCP server. But otherwise, I didn't hit anything on the keyboard. It just goes through, runs DHCP. It got the file name to boot from the DHCP server, and it's booting it. It downloaded the script. It's now downloading the kernel image required by the script. And it will, after that, download the initRD. Let me grab my laser pointer device. And now we have the initRD. What it's booting, by the way, is called Tom's Root Boot. It was a popular diskette-based Linux recovery CD back when kernel 2.4 was new. So the advantage is that it's extremely small, very suitable for booting over the wide internet.
The web server that it is booting off of is in Portland, Oregon, at Oregon State University. And the speed that you see it downloading and booting right now is comparable to what a floppy disk would take, 8 years ago when this was a popular thing. Let that go. What it's doing is it's probing for a PS2 device that doesn't exist. In about 4 seconds, it'll give up and wander off. Yeah.
Because this was before USB was common.
Yeah, this is 2.2 Linux kernel.
And we have a Linux shell. This could be used if you, for instance, needed to mount your root partition to change your root password or do some other similar diagnosis. You would get, you would be able to do that with something like this. You probably would not use this one because it's very, very old, but there are newer ones. OK, that's that demo. You can see it's running completely out of a RAM disk. DevRAM 0, DevRAM 3. This was modern Linux kernels don't use this RAM disk interface. They use something called RAMFS, which is more flexible. But there is no root partition here that except for what was loaded into memory by gPXE, the initRD that the kernel ran from. So that's one way of doing things. You can also have it mount a SAN partition, which we're going to show you in a bit. RAM 3 was basically, it was just, it created two RAM disks, one to use as the root partition and one to use as the temp partition. So that the temp one was smaller, so that runaway process writing temporary files couldn't crash the whole system. Okay.
These days you're using a init RAMFS instead.
Next demo is, sorry. Okay. Next demo is the deb-Athena network installer from here at MIT using HTTP. So I basically, at MIT, if you boot a vendor PXE stack, you will see a menu that goes, you want Windows remote installation services, if you want deb-Athena, if you want gParted, etc. And I'll show you that later. One of those options is a network installer that will start a deb-Athena install without a CD. This is used extensively in the clusters here. It answers one of those questions that we talked a lot about earlier, which is how do you set up identical machines without driving your administrators crazy. But to give an example of how gPXE might be used, I took the same files and reconfigured them very, very slightly to work with an HTTP boot. I apologize for the video mode switching delay with the projector here.
That's unforgivable, Josh.
So here we are just loading straight up a PXE Linux.0, which is the main PXE Linux boot file, out of a folder called o2debinst on the web server. This computer, by the way, is called jake.in.etherboot.org, where the .in, etc. is internal DNS. We restart. DHCPD. Don't forget to do that. I've forgotten many times doing stuff like this. And reboot the computer. Initializing controllers, checking memory, and we'll get gPXE in a RAM disk, or in a ROM. By the way, that press Control B to configure prompt is mainly used if you have a network card where gPXE supports storing settings in non-volatile memory. We don't have a demo of that because we don't support many cards for that yet. But if you have a card that's supported, like a Realtek 8139, you can store something like a username and password in there so you don't have to send them over the internet. And here we have the deb-Athena network installer. I don't know if you saw it going by. It loaded PXE Linux. PXE Linux very quickly loaded its configuration file and the kernel and initRD that it was asked for. It's a local gigabit network, and it's running over HTTP, so it's extremely fast.
So you're saying that machine just booted from some random machine on Athena?
No, yes, exactly. It loaded the initial files off of this web server,
Right.
and then went to athena10.mit.edu to fetch this deb-Athena jaunty.tar containing various instructions like this. If I were to continue, it would realize quickly that I don't actually have a hard drive I can install onto, and there would be trouble. So I'm going to stop it here. But this gives an example of how this can be used.
Network admins aren't going to have to carry nearly as much stuff as they used to carry around with them.
Exactly. Next, I'd like to demonstrate a Linux iSCSI boot. So this is back to that SAN use. And you can see in our dhcp.conf, we have this root path option, which with that crazy long IQN name, which asks for a disk to be accessed on the server. I'm going to set that, restart dhcpd, restart the boot machine. I said restart.
Well, that's reset. The power button's on the
Yes. Here we go. The gPXE in this machine is flashed into an Intel Ether Express 1000 card. This is a very popular card for gPXE because it has a 128 kilobyte EEPROM. So you can fit large images in there if you can load them into your BIOS. I don't know if you saw it flash by. It executed the SAN boot very quickly. It didn't have to load a lot from the hard drive. It just set up hooks so that when the grub bootloader was trying to access its hard drive, it would actually go through gPXE to access the network. And the speed is completely comparable to a normal Ubuntu system booting up. We actually, when I was prepping the demos for this talk, we had the, it's been 180 days since your file system was checked, check forced, and the FSAC went extremely quickly. So, and you have a normal Ubuntu system, which you could log into. Let's see. I think I created an account for myself on here. Yep. The login is nice and quick, well, as quick as Ubuntu ever is.
And
I'm going to.
The cool thing is that the second time you do, things are much faster because the iSCSI server caches so much.
And if you have multiple clients booting off the same server, loading the same image, that can be a very considerable speed benefit. Here you can see I displayed the SCSI information from the ProcFS. The only SCSI disk in this machine is an IET virtual disk. IET is the iSCSI Enterprise Target, which is the name of the iSCSI server that's running on here. It's a free open source program, works great. And it looks like we're running off a hard drive because our root file system is dev SDA, but that's actually a SCSI device created by the kernel component of an iSCSI initiator in this system.
Can you do a netstat - tn?
Oh, yes. And you can see everything's come up. Sorry, here we go. And this is the connection that's basically the lifeblood of this computer right now. It's connected to port 3260 on .53 is the server. So if this were to go down, the root file system would basically disappear and the computer would probably crash. Thankfully, there is a lot of redundancy checking and attempts to reinitiate the connection and so forth that are built into the iSCSI code. So this computer, you could run basically anything that you would use a normal Ubuntu system for. It just doesn't have a local hard drive. Next, I'm going to demonstrate a DOS memdisk boot. DOS is probably used more often in network booting than in local booting, just because it's an extremely simple system, and it's also great for us to test with, because it doesn't have its own disk drivers, so it uses gPXE's drivers the whole time. If you do an iSCSI boot and you run ScanDisk, that's actually our standard stress test of a new network driver to catch any memory corruption and such. So memdisk is a part of the SysLinux suite. It lets you create a virtual floppy disk image and export it to DOS like it's real, just in the same way that gPXE lets you export a network drive to the early boot process as though it's real. And for that, we're going to edit dhcpd.conf.
Make sure you do a clean shutdown of Ubuntu.
Yes. That's the other thing. Since this is not using the copy on write technology, if you were to shut it down uncleanly, the next time you tried to start up from this image, it would do a file system check, just like you're used to on a local drive. So shut that down. Wait.
This is much more interesting when you have 50 computers hooked up to a server.
Yeah, we're only demonstrating with one, but when you can start all 50 at the same time and the server is perfectly able of handling the load, it's a real demonstration of why this stuff can be so useful. The particular, here I'm loading a gPXE script over TFTP because there's no HTTP specified, and TFTP is the default for net booting. If I look in TFTP boot, you can see this ibautil.gPXE. It loads ibautil.image as an initRD, and then chain loads the memdisk, which is packaged as the Linux kernel format, with this option raw. We actually tried it without the option raw at first, and this had worked for me on my home system. But I guess the BIOS on this system has some issues with how memdisk and the flashing utility interact. So raw was necessary to resolve that. This stuff can be kind of low level, and you play around with it until it works. But once it works, it almost always stays working. So, and in ibautil.image, oops, sorry. Yep. We have some special utilities. ibautil is the DOS mode Intel boot agent utility that can be used to reflash an E1000 NIC. It's another reason why we like E1000s. And we have some ROMs on here. 808.6.107c.iba is the ROM image that was created for this network card for gPXE. Since we have some time, I'd like to demonstrate a site called ROM-O-Matic, which is a very nice feature of the Etherboot project. And this is basically Marty's baby, the ROM-O-Matic site.
Shall we pass around
Sure.
an E1000 card?
Yes.
This is an Intel E1000 card that you can buy at Newegg or wherever for about $30. And we have replaced its firmware with gPXE. We can do this for BIOSes and a lot of things. And this is what we're demoing most of our demos off of. It's a standard run-of-the-mill gigabit card. Intel makes a very nice one. The feature that we like most about it is that it has very ample flash RAM, EEPROM flash on it. 128 kilobytes. That doesn't sound much because it isn't. It's about 1/8 of a floppy disk.
For network booting, that is a positive island.
Right.
The largest gPXE it's possible to make with one NIC driver, which is like with one of the really huge wireless drivers and all the WPA and everything enabled, is less than 128 kilobytes. So we love ROMs like that.
But it also means that we have to write our code very conservatively. Josh is the master at writing small code. Whenever he submits a feature to the main branch of gPXE, he always gives a count of how many bytes of increase in size it will add to our ROM. We appreciate that.
So this is ROM-O-Matic.net. And this is...
Control plus.
Yes. OK. This is... sorry, the left side is cut off a bit. This is a site that helps people who aren't interested in installing an entire development environment. gPXE is pretty easy to compile by hand. We have instructions on our website, etherboot.org. But oftentimes you don't need to. If you want a ROM image of the type you could flash into this network card, you might say ROM image. This is an E1000. The gPXE driver names generally have a one-to-one correspondence with Linux kernel module driver names, so it's easy to find that out. If you're confused, you can check on our website. It's 808.6.107c, but I'd like to show you how you get these. If you're on your system and you run lspci-nn, well, wait. This is an old version of PCI utils, I guess. This is, by the way, this machine runs Fedora Core 6, so pretty old, but it still works great. If you run lspci, you can find your Ethernet controller. For instance, we have actually two E1000s, or actually it's one card with two ports in here. And that's 02:09.0 on the PCI bus. And then you give it the -N. The PCI IDs for this card are 808.6.1079. And as I mentioned earlier, you need those PCI IDs so when the BIOS is doing its ROM scan, it knows that the ROM on this card was actually meant for this card and is not corrupted. So you enter those. You can customize it a bit. I'm going to enable HTTPS support. Wait a second. The checkbox is off the screen. Let me check that. I've not used the AV systems at MIT before, so.
Yeah, I think that.
Sadly, there does not appear to be anything.
Are you looking at you're not looking at this monitor at all, I take it?
No.
Okay.
Yeah, this does not have it, sadly. Okay, well.
Hold on, I think I can pause it to resync.
Actually, if you could just unplug the projector for a bit and plug in the monitor. It only supports having one plugged in at once.
Okay.
Or just leave the monitor
Ready?
in. Okay, wait.
Hold on. I got it. Hold on. There?
Yes, okay, now and I did succeed in selecting HTTPS, so just unplug,
Okay.
plug back in the projector, leave the monitor.
Got it.
Thanks. You can look at the monitor in the meantime if you want. Here we go. Yes, excellent. Okay, so you can select download protocols, SAN-boot protocols, iSCSI and AOE, as I mentioned, whether you want the DNS resolver, which is included by default, various supports for different types of images, you can selectively take out some of the command line features if you want to save space, and you can put in an embedded script. I'm going to leave that blank because we're using DHCP for everything. Then you hit get image. It goes for just a bit. And you have a ROM to save. And you can save that wherever you like. I have a ROM already on this image, which I'm going to use just in case there's a slight difference. But having configured dhcp.conf and restarted dhcpd, I can show you how this works. We have our boot process again. I'm first going to flash the vendor PXE back onto the network card and demonstrate PXE chain loading, and then flash gPXE onto it again. And we're in DOS. So I can do dir. I have IBA util. You can get help. And you might notice the dash install will program the default Intel boot agent image into the flash on the selected NIC. Dash restore restores a previously saved image, or restores or flashes a gPXE image that was cleverly named to be the same as the name with which it names its restore images. So I'm going to use dash install. And it's done. And this card is now flashed with vendor PXE. If I reboot.
You're programming Ethernet cards?
Yes, I'm programming Ethernet cards live, only at MIT.
Live, only at MIT, that's right.
And it's the Intel boot agent this time.
It should be noted that ROMomatic.net was created in 1999. And over the course of the last 10 years, we have generated over 2.5 million free open source ROM images for pretty much 100 different Ethernet cards. So it used to run out of a DSL connection in my basement, but now it's at...
So you can see here, it loaded the vendor PXE and then chain loaded gPXE because the DHCP server saw that there was no user class and so served up the undeonly.kpxe image. If you want, I will demonstrate, how that is configured. We have down at the end here, if not exists, gPXE, well, this here it's going on the bus ID. You could also say if not exists user class, then provide file name of undeonly.kpxe. We configure our hosts here so that if someone else should happen to connect to our network through some means, they won't get strange network booting. But now that I am on InDOS, I can IBA util dash restore, flashing, and
Oh, I know what the problem is.
done. So if we reboot again, you will see that we come up with gPXE.
Look at that.
I'm going to break to the gPXE command line for a bit so that I can okay, this is the command line. You press Control-B where it says to press Control-B, and you have various things you can do. This is the same as what I showed you in the scripting earlier. This is often useful for debugging. Like if you want to see whether gPXE recognized your network card, you can say ifstat, and it will tell you all the network cards it sees in your system. This system has 2 network cards. It has an E1000 and a Realtek 8139. But to save space in the ROM image, we only included the driver for the E1000 in the ROM for the E1000, so it only sees that one. Gives you its MAC address, PCI, bus ID, etc. Now I'm going to bring up our next demo, which is a demonstration of authenticated booting. This is from a proof of concept that was written by Michael Brown, our lead developer. And you can see it's going to boot over HTTPS from this boot.php file, and I'll show you what's in that after I demonstrate how it works. I'm going to say auto boot to start the booting process back up, as it would have if we didn't go on the command line. It runs DHCP, and boot.php runs a special gPXE command called login that brings up this screen. And you can type something like J, I think it's password, and enter. It will check your authentication, and only if you enter the correct username and password, it will offer you a menu of options. If you did not, it will offer you only one option, try again, which will take you back to the login screen. But from here, you can boot anything that was configured on the server. I'm going to demonstrate an iSCSI boot of Windows 7. Yes, we boot anything we're given. It is in fact possible to install Windows 7 directly into an iSCSI image. You have to install it off of the DVD, but you start it up from gPXE in a way that's described on our website using the keep san command, and it keeps the information about the iSCSI disk around in the iSCSI boot firmware table. The installer finds that, makes a connection to it, and provides us a drive you can install onto. Yes. Here we go. And welcome to Windows 7. As you can see, this was quite a fast boot up. I mean, obviously, these computers are directly connected, so it's going to be fast. But even on something like MIT's campus-wide network, booting is very fast. I'll demonstrate that later. Actually, I guess we should properly shut down Windows 7.
Yeah.
Give it the respect it may or may not deserve.
Faster distant.
Yes. And just to keep you on track, that was authenticated boot menus. And I'm going to show the code from that, because it's pretty neat. We have boot.php here. Boot.php prints, it basically outputs a gPXE script, which runs image-free to get rid of the script. This used to be necessary. This demo is from an older version of gPXE. This is now not necessary. It used to be that if you were using a gPXE script, the script itself might be loaded as an initRD, but that was a bug that we fixed. Login brings up that menu that asks for username and password and sets the gPXE username and password settings. And then we chain load the username : password at our server / our directory / vasemenu.c32 and pass menu.php as its argument. Vasemenu.c32 is a syslinux module which provides a nice looking menu. And it reads that menu from its argument, menu.php, which is another file which contains the real interesting stuff that shows the menu. The only reason this was made a PHP file instead of just being a static script is so that it can maintain workingness even if you move it around, because it can use these variables. Note the :URI string interpolation. That causes special characters in the username and password to automatically be escaped into the % escapes for URIs so that gPXE doesn't get confused. Well, if you were to, say, enable a password on your BIOS and change the banner timeout to 0, that was a configurable option on ROM-O-Matic, which determines how long the press control B for gPXE's command line is set, then the user would not be able to do anything other than go through this process. And if they entered in incorrect login, data, they would not get anything useful in the menu that they could boot. Here's the menu. This is, I'm not going to go into too much detail because we have about a half hour left and some cool stuff I want to show more. But this basically, this is straight from an example on our website. And it has PHP functions that make things a little more obvious down at the end that defines the policy, where it outputs code for the basic menu syslinux module. So you can check, it checks against these username password combos, and then you can decide different images to show based on the username. It's PHP. It's a program running on the web server. You can do whatever you want. And
rather than serving a static file, you're actually serving a file you generated.
Exactly. See, in this case, you can see, sorry again about the cutoff on the left. This is what it generates if you try to do it without any authentication. It will say, authentication failed, and your only kernel option is load boot.php to try again. But if you pass proper authentication, actually, I'm sorry, this is a issue with Firefox, that it will not actually pass your authentication unless the server gave a 401 message. So I can't, I guess, demonstrate that as well. But it was obvious from the demo that there was a different menu loaded and it worked. OK, so next up.
The reason your right side is, or your side is cut off is because you're 1280 by 1024 rather than 1020.
Let's see. Can we fix that on the fly?
Yeah. Display or something like that. Yeah, system. Can you run XR and R?
Yeah. It's probably not worth it.
Okay.
Oh. Excellent. Thank you. OK, much better.
Tasty. Thank you.
That's better, though.
Yeah.
OK. So we are back in our dhcbd.conf. I am now going to demonstrate a distributed internet net booting service. There are two of them, primarily. One's called boot.kernel.org and is maintained by someone who worked with gPXE on Summer of Code and one of the gPXE developers. The one I'm going to show you is called netboot.me because it's easier to chain load from gPXE. This was created by some guys at Google, Nick Johnson, I believe. And it is a very polished and quite awesome demonstration of some of the power of network booting. They have actually forked slightly gPXE to apply some experimental code that was developed for Summer of Code but has not yet been integrated into our main branch because of size concerns.
He uses the advanced scripting from a Google Summer of Code project that we haven't merged in yet.
So here we're chain loading the undeonly.kpxe from that slightly enhanced gPXE, and it's going to show you a netboot.me menu. So
Thanks for coming.
bye.
Bye.
And we have loading. doing DHCP. You can press space at those Control B prompts to avoid having to wait. It loaded the undealing.gPXE. It's now downloading stuff from netboot.me, and we have their pretty polished, I think, menu. You can pick graphical or text, boot a configuration by number. If you do graphical, it'll download basic menu and present you with this.
Oh.
You can have some games,
Extra
NetHack.
points for whoever knows what country .me is.
You can do a install of Ubuntu from this thing. It'll be slow because it's over the wider internet, but you can it's got you can load memtest86, all sorts of stuff. Yep.
I like
And
the progress indicator on that.
And here is a memory test as an example of some of the diagnostic tools that netbooting can be useful for. In this case, you didn't even need to set it up. If you go to netboot.me, they have USB stick, ISO, and floppy images containing their modified gPXE that you can download to use their service. So that's pretty cool. Now we're going to move over to the netbook and show you an encrypted wireless boot.
I should make the point that this is like really cutting edge. No one actually attempts to do this. No one actually attempts to network boot. We're the only software that will do a network boot over 802.11. So, and Josh wrote it this summer. So this is very cool. On most things, you would have to load an operating system in order to even attempt something like this.
Okay. I selected the BIOS boot selection menu on my EPC so that I can boot off a USB stick. Because there are no floppy or CD drives, you can write gPXE to a USB stick. There are instructions on the website. Yes, that's the Ethernet that's built into the BIOS. However, that will not be... No, sadly. However, that will not be sticking around for the entirety of our talk today. So we have this gPXE boot. This has and it looks pretty... It looks like it's working totally fine. It's in fact doing the same netboot.me demo. So the problem here is that the wireless doesn't interact very well with PXE chain loading, so I need to enable a different demo. This wireless doesn't use PXE. There are no vendor PXE ROMs available on wireless NICs.
Yes.
Exactly. I mean, presumably it could be stored in non-volatile memory or something, but the problem here is I forgot to restart DHCPD. This happens fairly often.
Well, I will promise to restart DHCPD.
Thank you. Thank you very much. Okay. Have our boot. And net 0 is the wireless interface. As you can see, there is no Ethernet cable plugged into this laptop. It's booting off of DOS iSCSI. And you can do scan disk. I mentioned earlier that's a good stress test. But, well, are you sure about that? 'Cause I'm not.
You may be freaking out over the video mode. It is a freaky video mode.
Okay, allow me to display for you. We're doing a surface scan. And you can see blocks. Yes, here we go. So it's actually talking to the iSCSI server on that computer, and
through this wireless interface.
And if I let it stick around for long enough, it would examine the entire hard drive. Obviously, wireless is slower than wired, but it's not unusably slow.
Oh, but Josh, look at all the flash.
Yes.
The fast-blinking, flashy lights.
I'm going to exit out of this and go back to our demos.
Okay. I went to channel 1.
Okay. Wait. Where did... Oh, sorry. This thing is useful.
Okay.
Next, I'm going to show a Windows AOE boot, but instead of just getting to see Windows boot up, you get to see it doing something cool. Now, this is AOE. An AOE root path is pretty simple. It's just the E shelf.slot. We have the AOE server called vBlade running on this machine. vBlade, just like IETD, is open source and freely available and pretty easy to use. So I would first like to, let's see, it's 6:45. Yeah, there is a lot that went into this demo, and I was hoping to show you more of the details of it, but I'm not sure we're going to have time. Basically, what I'm going to do is I'm going to boot Windows and use it. Sorry, I need to restart DHCPD. There we go. OK, I'm going to boot Windows and use that Windows instance to splice a gPXE image into the BIOS for my netbook. I downloaded it off of the ASUS website. It's a 512 kilobyte ROM file, and it's an AMI BIOS, so I can use the AMI BIOS modification tool called mmtool to change the option ROM images in there. In order to get this working, I had to modify the gPXE source somewhat to make some options that are by default always included able to be compiled out. Things like PXE support, which would seem to be a pretty basic part of a program called gPXE. However, I was, in the end, able to get a 70 kilobyte ROM image that includes a complete wireless networking driver. So I have that ROM image on this Windows disk image, and I'm going to show you how it is pasted sort of into the system BIOS. I'm then going to take that BIOS and flash my netbook.
It's much more dangerous than it sounds.
Wait a second.
That's true. It's only a $300 mistake if you blow away your...
I think we lost USB.
Oh, just pull out the USB connector and plug it back in.
Yeah.
Yeah, I'm sorry.
This KVM switch can be a bit finicky about its USB.
Yeah, it is. Click the mouse and...
Fail.
Hold on. Yeah, I'll get it for you.
Thanks.
Which one is it? Yeah, just pull out the USB cable here. Let Windows...
No. Well, that's...
Flip to a different channel and then flip that.
Here we go.
There you go.
OK.
Yeah, Windows takes a minute to notice these things.
Now, so
Okay.
this is mmtool. I don't know how well you can see it. I can just change the resolution, actually.
Yeah.
Here we go. OK, that's visible. This is mmtool. I don't think it's pretty easily accessible. Just Google for mmtool. I'm not sure it's available from the manufacturer's site or not. I think they like to discourage this sort of thing. But I have my ROM image. This was downloaded, the latest version of the BIOS for my netbook from asus.com. I load it up. I have some PCI option ROMs in here. And you can tell what it's for based on the run loc, which gives you PCI IDs. This one is 8086 something. 8086 is Intel's vendor code. So that looks like the video card because it's not a network card ID I recognize. This one, though, 1969-1026, is the PCI ID of the Atansic L1E Ethernet card that is built into the motherboard.
Wired.
It's wired Ethernet, yes. So I don't want that anymore. I want to put gPXE in there. So I'm going to hit replace, load up this, and replace. The name, by the way, this 1969-1026-F5K, that is the gPXE build system chooses the type of image that it gives you based on what the name of the file you ask it to make. So eight hex digits is used for a ROM image. A driver name is a driver. If you put multiple things in separated by dashes, it'll be a ROM that has all the relevant drivers, but uses the IDs of the first thing. So this is a ROM image that supports both ATL1E and F5K, but looks like an ATL1E ROM, so the BIOS expects to find it on the ATL1E card. The .HROM is high ROM. That's a prefix that I created for this. It works around a limitation of the netbook's BIOS. The netbook doesn't support PMM, the post memory manager that I mentioned earlier that helps get around some size limitations. This sort of forces to use a slightly less safe way of doing the same thing. And I now have my ROM image. I can save it as this thing and go back here.
This is basically impossible.
And download it over Samba. Foo is the password. I'm just giving anything. And then copy that file onto a DOS iSCSI disk with the Asus Flash utility, which I've already created for you, and flash it. So it so happens, in fact, that this DOS iSCSI disk is the same one that I just booted earlier, and may even still be up, actually. So if I switch over to netbook, yes, I'm still at the C prompt.
Yay.
And I have this directory called Flash. How wonderful. And I've run AFU236U, ASUS, AMI firmware update 2.36. I don't know what the U stands for. /I for input, ASUS gPXE.ROM, which is what I named it to fit in 8.3 naming conventions. Warning, do not turn off your power during Flash BIOS. Reads the file, reads the Flash. This, by the way, is flashing wirelessly. I do not have the ROM on that USB stick. I can pull out the USB stick, but I'm not sure I should.
The man is just fearless. Is there power plugged into it?
No, it's running off its battery.
Are you sure it's charged?
Yes. And while this is running, I'll take any last questions. I have one more demo after this, and then I'm going to talk a bit about the future of gPXE, and then I'm going to let you all go. So are there any questions? Any are you insanes?
He's sane, I think. But basically, what you saw was somebody inserting an open source binary option ROM into the BIOS of their netbook, and then reflashing their netbook using a DOS that was booted wirelessly. About half of those things can't be done in any other way than what you're seeing them done here. So this is pretty.
I'm going to take out the USB stick, boot up the system again.
Thrilling, but out there.
And when it comes up, yes, it did come up. I'm going to pick the boot menu again. And look, it's a gPXE ROM.
So the BIOS now contains a copy of gPXE.
And instead of authorized boot agent, we have gPXE on PCI 0300.0. And if I let it go, it will connect to MITnet, do DHCP, fetch a gPXE.NBI off of my personal server, which image will do DHCP, And it was supposed to access the iPXE menu from MITnet, but I guess that isn't actually exported to the wireless network. Oh well. I can demonstrate that on the wired system if you like. So yes. That is...
Oh, we all right?
We're fine.
Okay.
Okay. So yes. That is wireless iSCSI. And I have one more thing. This is something I've been working on very recently, actually. It's a modification to gPXE to support SAN-booting ISO images. And the ISO, this is normally kind of an esoteric feature because then the ISO image would, just like any SAN disk, have to contain the appropriate startup code to handle the pivoting to the OS accessing the SAN. But I did that for a very particular live CD, which will be of interest to some people in the MIT community, namely the Debathena live CD. So start this over. I go over here. I need to shut this down properly because it's Windows.
It wouldn't probably do anything worse than if you yanked the power cord
Yeah.
out of a running PC, but
Exactly.
that's cool.
Because this is sort of an experimental feature, what you saw here was me chain loading a new gPXE. And here you go. It did an iSCSI connection to a XVM that I have running. And it's basically, this is exactly what you would get if you stuck the Debathena live CD in your computer and started it up. And I'm going to keep going because this is a good demonstration, I think, of the speed of this stuff. It'll actually boot faster than it would if you were running off a CD.
It should be noted that there's no other network bootable way to network boot a CD. The reason there isn't is because every time a CD starts up, the first thing that the CD tries to do is access its hardware. So you have to get around that. How did you get around that?
I basically, the same way that a hard disk boot works, you just have to trap a couple more BIOS calls. And you have to modify the initial RAM disk on the CD so that it knows to look for itself in more places. Ubuntu is nice like that because its initial RAM disk actually is already extremely flexible. It supports mounting the CD image out of NFS, out of some other places, so I just added iSCSI to that. And now I can log in using my Athena account. Yes, I pre-registered this machine on the MIT network. Oh yes, the existing code for handling the NFS situation disables Network Manager. You can say it's all not managed. But this is my Athena setup. I have all my files on my desktop. This is my Athena home directory. And I could use this machine now basically just like an Athena cluster machine. So, and you saw the speed was perfectly acceptable. This is probably the most, well, that or maybe the netbook reflashing, is the most advanced thing I know how to do with gPXE. But you all have great imaginations and great skills. I'm sure you might come up with stuff that's even better. Sorry. I need to wait. Oh, over here. Yes. So that was Network Debathena Live CD. Now, before I wrap up, I would like to take a few minutes to talk about some of what's going to be coming in the future. Some stuff that we're working on now, active development for gPXE, includes better scripting, the ability to have scripts that do things like if and while and boot try all interfaces, boot from the first one whose number is whatever. You could basically, anything as complex as you could express in a shell script. The main blocker on that is code size, but we're figuring out some tricks for that. As I demonstrated before, SAN ISO booting support required some re-architecting for the gPXE code base because there used to be a big distinction drawn between loaded images and SAN disks. And we had some ISO booting code, but it only applied to an ISO image loaded in memory, and that wouldn't be practical for a 600 megabyte image. So we had to unify that. We're thinking about making sort of the ability to fetch additional modules for more functionality off the network. So if you had some ROM size constraints and you wanted to be able to do an iSCSI boot, maybe you could load an iSCSI module over HTTP because iSCSI is huge and HTTP is a little smaller. And better documentation. Some things that are more out there may or may not ever get implemented but are cool to think about. Being able to load files out of file systems on SanDisks. So have a little X2 or whatever driver in gPXE that could look in the disk and load a different kernel or something, so you wouldn't have to rely on grub. A feature I'm working with SIPB with is the ability to boot your XVM on a local machine. If you have installed the iSCSI initiator on it, you might be able, that might be useful for testing or something. And some finally things that are just ideas at the moment. The ability to have some sort of centralized way to create a net booting environment so that you could have a server that had common images, would use the copy on write technology to give everyone a personalized way to do that. But you could basically get a new Athena cluster-ish machine of just about instantly by creating a new cow file off of a central SAN bootable Athena cluster image. Or a new Windows machine using the MIT site license or something like that. And the final thing, Josh's crazy virtualization idea. The issue with SAN booting an ISO is that the ISO has to know it's SAN booted so that it can go looking for its iSCSI host. A lot of things that people would really like to be able to SAN boot, such as Windows install disks, don't know that. So it would be interesting if there was some way, almost certainly not integrated into gPXE itself, to create a very thin virtualization environment using the hardware virtualization features on recent CPUs to basically pass through every device except the add a virtualized CD drive and don't pass through the network card, so that the installer would believe it's executing on a perfectly normal piece of hardware, but when it calls out to its CD, it's actually going over the network. So that would be an interesting way of solving what's been a sysadmin dilemma for a very long time. But maybe not so practical, but fun to think about. And that's basically it. There's a lot more information available at etherboot.org. If you think this stuff is awesome, get involved. Talk to, if you're from the MIT student, talk to SIPB. I'm working on some stuff here. We may have other people too. If you're a student, you can work for us in Google Summer of Code, get paid a bit to work on this stuff if you really like it. And again, a big thank you to Marty Connor for his help with the demos, with organizing this, and videotaping also. So thank you very much, everyone, and I hope you enjoyed the talk.